If you don't remember how many you took, pay everything. Okay. You always have more than you remember. Yeah, absolutely. I subscribe to this point. Okay, so let's be back to field quantization and all that. So we are basically finished with field quantization. We learn how to quantize the field. We examine the Fock states, the current states. We discuss phase space distributions. We will see a few examples of those, most probably in the next lecture. And we studied field relaxation. And we got interesting results. We got that a Fock state decays by not staying a Fock state, but the current state decays by staying a current state. And by the way you measure the relaxation rate in an actual experiment is just to send a current state and look how fast the energy or the amplitude goes away. Kappa over 2 for the amplitude, kappa for the energy. And we have also seen a very puzzling result that the current state doesn't change when it loses a photon. I think I ended up with a small riddle. How can you save the planet by extracting energy out of a current state? So clearly it doesn't work, because I would be already preparing my package for Stockholm. The Nobel Prize is to be announced next Tuesday, 11:45. So since it's not the case, do you have any idea why it's not possible? Has anybody a solution to the riddle? Yes?
I think it might just be in the normalization terms of the trace.
I would like something more physical as an explanation.
So you cannot develop a machine which which fulfills the Lindblad master equation without having the trace normalization terms, and
there's something to your argument. Yeah, I'm not sure I fully comprehend it, but there is something there. Anybody else? Yes?
So, I mean, I programmed it today, and I saw if I calculate the Monte Carlo wave function for this trajectory and just plot the mean photon number, it reduces exponentially, which is not like in steps. It means the jump operator.
No, I agree with the Lindblad function. But what I was asking is, this is the situation.
I know. So the jumps.
The jumps are not seen.
Yeah, you can see the jumps, and this means there's like the non-emission part of the
Okay.
equation.
Yeah. I think you are both on the line to solution. So the basic idea is that I have a perfect cavity, no relaxation at all. I have a current state alpha equal 3 inside. And what I say is that I get a photon off, I don't change alpha. And this is true. You have seen that numerically. And of course it's true because alpha is an eigenstate of A. Cannot be else. So how could you extract energy out of that? You have to think of a machine. And the machine would be simple. You would have a cord and a bucket at the end of a cord. And in this bucket, you would, for instance, put an atom. You would lower the atom in the cavity. It's resonant. It can absorb a photon. You take the bucket off, and you look at the atom. If it's excited, Jesus, you extracted the energy, you can use it. If it's in ground state, you lower the bucket again, and you restart. The key point is, when you do extract the atom in the upper state, you get the energy, and you get it for free, because that, you can put that in terms of atom field interaction. You will have all the elements in a moment. You can make a detailed model of that. You get the energy, but what basically acts on the current field is A, the annihilation operator. So when you get the energy, you don't change the field. But each time you fail to get the energy, each time you extract the atom in this ground state, you know something about the field. You know that there are less photons than you expect, because it's the non-emission part that is acting. So when you succeed in extracting the energy, you don't change the current state. But when you fail extracting the energy, you reduce its amplitude. And at the end, you can work an explicit model with atom field interaction, kind of Cavity Qed arrangement. I once gave that as an examination problem for the master degree at ENS. And there's a whole generation that is hating me for that. But nevertheless, the amplitude is reduced when you fail extracting the energy. And at the end of the day, if you compute the mean energy that you extract, it's exactly 3 times h bar omega. Okay? Which doesn't mean, of course, there are fluctuations in the current state. Take a current state with 10 photons, send it on a 50-50% beam splitter. You get, on the average, 5 photons in each arm. But put 2 photon detectors. If you are very lucky, you can find 30 in one arm and 125 in the other. Because the P of n is a Poisson distribution and it extends to infinity. Okay, you need to be extraordinarily lucky. So for all practical purposes, it doesn't work. It's like making your life out of playing the lotto. Generally, it doesn't work. That's okay for the riddle? It's when you fail getting the energy that you reduce the amplitude. Because you get some sort of information. We tell you, most likely, there is not as much energy as you expect. You can put that in this term. Okay, so I would like to quit these amusing riddles. Hope they are amusing. And to get back to the atom field interaction. We have a quantized field. I want to interact a quantized atom. Obviously, atoms are quantized. I want to interact a quantized atom to go a bit step further than Philippe, who is considering up to no classical fields, which for 1 watt laser is perfectly justified, and to get into the atom field interaction. It will work, just a second. So I would like to consider, I will do less than there on the notes. I won't address the photo detection problem. You may look at it and ask questions if you wish. We just get to the spontaneous emission and the dressed atom model. So spontaneous emission is basically computing what Philippe has been telling in his 2 lectures. I have an atom. It has an excited state. How fast does this excited state decay due to the coupling of the atom with a vacuum radiation field? Obviously, the atom will emit a photon and will decay. The good news is that we can play it a 2-level system. Because when an atom has many, many levels, it can decay through many spontaneous emission channels, generally. But all of those spontaneous channels have rates that just add up. Just because there is no quantum interference between the channels, just because their final states are different. So if you have an excited state, you can just add the rates of decay to all the states lower. Add the rates of decay to the degenerate states in the ground state and everything. So we just need to consider a 2-level transition. So we will write the atom field Hamiltonian. This will be useful later. We'll solve the Schrödinger equation using the Wigner approach. And we will compute the emission rate and the energy shifts. I will skip a little bit of the hairy algebra in all that. You have that in the notes if you want to do the calculation yourself. So what is the atom field interaction? Well, if you take an hydrogen atom to make things simple, you would start with the hydrogen atom in an electromagnetic field. So you have a Coulomb potential, you have the V of the incoming field, you have the IA in the incoming field that modifies the momentum of the electron. So this is the basic Hamiltonian, and this Hamiltonian is totally untractable because it's quadratic in the field. But fundamentally, it's quadratic in the field. How do you cope with that? Well, you expand that. You get a term in P square. That's neat. So you just get the free Hamiltonian of the atom. You get PA and AP, and you take care of the commutation rules because A has a position operator for the electron here. And you get an A square term. And you say, well, if the field is not large enough, A square is negligible. This is absolutely true for all practical optical fields in laser experiments. The laser power of 1 watt, it's infinitely lower than the threshold to see. It's clearly totally false for the petawatt lasers, or things like that. In that case, it's the A square term that dominates totally the evolution. And in fact, this dominates even the Coulomb potential. But we are not in that case, so I just neglect the second order terms, and I make also the dipole approximation, which is basically assuming that the atom is a point at the scale of the incoming wavelength. And this is very true because an atom is typically 1 angstrom. I love this old unit. The angstrom is a 1/10 of a nanometer. It's totally illegal. So an atom is about 1 angstrom across, while an optical field is 1 micron across. So you have plenty of space. So it's a very good approximation. And you work that out. It's a bit lengthy, but you get 2 possible forms for the Hamiltonian, for the interaction Hamiltonian, minus Q over M P dot A, where M is the electron mass. It's called the AP form. And the most familiar dipole electric form, minus D E, where D is just the product of the charge of the electron times its position. It's obviously an atomic operator. So we have these two forms, and of course I will use only the second. Okay. So the derivation of that takes a bit of time. There is a beautiful Goeppert-Meyer unitary transform in the road. It's amusing. So how do I treat the atom field spontaneous emission in free space? I just write down the Schrödinger equation. I just write that I start in the state E naught. The atom is excited, I have no photons at all. And this state couples to all the states where the atom is in the fundamental mode G, and when I have one photon in any of the free space modes. So this sum is a big sum, many, many modes. And at any time, the wave function is of this form, C0 E naught plus some coefficients G1. Using that and using the interaction Hamiltonian, I just write down the Schrödinger equation for C naught, the probability amplitude to remain in the excited state. And I get this equation. There is an eigenfrequency, which is the Bohr atomic frequency, omega Eg, plus coupling to all the other states. And VL is just the matrix element of d scalar E between the initial and the final state. So I have and this is the converse equation for CL. I have an infinite system of equations, and I proceed to resolve it. The resolution is a bit violent. You have it in details in the notes. It's pure algebra. You have to switch an interaction representation to switch another interaction representation. Use a formal solution in terms of integral differential solution. Okay. At the end of the day, if you just define alpha naught, which is a rescaled amplitude for being in the ground state, just rescaled by an oscillating function omega Eg, you find this equation for alpha naught. It's an integral differential equation, sum 0, n of tau, a kernel, it is called a kernel, and alpha at time t minus tau. And n of tau can be straightforwardly computed under this form. Of course, you may explicit the VL square. Not really useful. It's a matrix element between 0 photon, 1 photon. So you have an A, you have to work that a little bit out with the expression of the field, with the expression of a dipole. More on that in a moment. But basically, you get that for n of tau. Let's keep the algebra. There is no physics in the algebra. Look at that. D square over h bar square. Okay, coupling square, of course. An irrelevant factor e to the omega Eg that oscillates. Okay, everything oscillates at the Bohr frequency. And here a big sum. A big enormous sum over all modes. And in this sum, an oscillating term at the mode frequency. So this is a sum of very many complex oscillating functions which spans all the frequencies for 50 Hz to the hard gamma ray. Because there are all the modes in this computation. So the sum here is certainly large at time 0, because all the oscillating functions are 0, are 1. But as soon as the time is of the order of 1 over omega Eg, of 1 over the width of the reservoir, it's once again a correlation time business, this kernel becomes 0. So for all practical purposes, in the integral differential equation, the kernel is a delta function. And if the kernel is a delta function, I can extract alpha, this is an alpha naught, sorry, alpha naught of t, and just be left with the integral over time of this kernel. Okay? And this is a standard differential equation. And the integral of the kernel, of course, is totally independent upon the atom. It's only a sum of all the modes. So what is left there is just a complex number. And nobody can prevent me, besides using force, to call gamma over 2 the real part, and delta the imaginary part. So at the end of the day, this is the equation of evolution of alpha naught. And remember, alpha naught is, within an interaction representation, the probability amplitude for being in the ground state. This, just say that this probability amplitude is decaying with a rate gamma over 2. The probability to be in the ground state decays, in the initial state, decays with a rate gamma. The probability to be in state E decays with a rate gamma. We get an irreversible exponential spontaneous emission. And what is delta? Delta corresponds to rotation of alpha naught. So delta is a shift of the atomic transition frequency due to the coupling to the vacuum modes. So this calculation was performed by Wigner and Weisskopf in the early 30s. It's a simple enough calculation. You can go a bit further than that. You can compute explicit, you can compute back all the coefficients by plugging this solution into the system, the differential system. You find, for instance, that the probability for having a photon in mode L at time infinity is just a Lorentzian function of the difference between the mode frequency and the atomic frequency with a width gamma. This is the kind of thing, Philippe, you have written all the time. An atom emits a Lorentzian spectrum centered at the atomic frequency with a width which is gamma. At the atomic frequency with delta. So we understand everything, and we can try to compute the kernel. So it's not that difficult. Gamma plus C delta is this integral. This integral sum of 0 to infinity of frequency is pi delta plus E principal part of 1 over omega. Standard result in distribution theory. You don't know what a principal part is? I don't know neither, but we don't care. Okay, it's some distribution. Okay, it's a hairy distribution which looks a bit like a derivative. And for the real part, you plug the, you find that, gamma. D square omega cube over 3 pi omega naught h bar c cube. And this is a very, very standard formula that pops out in all of atomic physics lectures. Gamma is like D square, you might have guessed it. It's like omega cube, because the higher the frequency, the higher the density of modes, the higher the number of modes. And, okay, this is just normalization. And you understand why microwave transitions have low emission probabilities, why UV transitions have extremely high emission probabilities. You understand plenty of things with that expression. The most economic way to get to that is to use Fermi-Golden rule. Compute the density of modes, of radiation modes, compute the matrix element, and use the Fermi-Golden rule. Gives directly that result. But what the Fermi-Golden rule doesn't give is the other part. Principal part, which is delta. And if you make the computation, you find infinite. The atomic levels are infinitely shifted in frequency by their contact with the vacuum field. And that, which was realized very early in the history of quantum optics, has been a severe hindrance to the quantization of the field. You get an infinite result. It's not the only one you get. We also already got the energy, the vacuum energy. But okay, you can say, I live on an infinite background of energy, and I don't care. This is more serious. An atom is infinitely modified by its coupling to the radiation. What is the solution? Well, it came rather late, 46, Shelter Island. It's in the middle of Long Island. When people discuss the lamp shift, which is another manifestation, a shift of the atomic levels, which is rightly that, and found a way to compute that, which eventually led to the concept of renormalization. So I'm not a renormalization guy. I cannot tell you how it works practically. The key idea is that there is not such thing as a charge independent of the vacuum fluctuation. The electron in the atom is not an naked electron. It's an electron already coupled to the vacuum fluctuation. And what you want is the modification of this coupling when you bind the electron with a nucleus, and not the coupling itself. And it works, and you can compute delta, and after that it works, it's QED. But there is very, very big difficulty. Fortunately for most atomic physicists, you don't care. Just say that delta is God-given, You go to the atomic spectra table, you read the value of the frequency, you tune a laser to that, and you observe a two-level atom, and gamma is right. This is the right gamma. Okay. So most of the time, we don't care. Okay? So I will skip the photo detection part. This is a bit boring, 3 slides thing. The key point is to say that when you put a photodetector in a field, the field operator that you are measuring is E plus E minus, which is precisely A dagger I, which is precisely the number of photons. We might have guessed it. Okay? Just a fancy way of getting that result. So now I would like to switch gears and go to the dressed atom model. This is a very useful model, not only for Cavity Qed, but also for cold atoms and for all of atomic physics, as we will see. And it's the model where you assume that the atom, instead being coupled to this awful continuum of modes, is only coupled, or is mainly coupled, to one mode of a radiation field. This is clearly the case, like in Philip's lecture, when you put the atom in a strong laser field. It's clear that the evolution due to the strong laser field dominates everything else. It's also the case in Cavity Qed, we'll define it later, but where basically you put an atom in a cavity and get only the coupling of the atom to one of the cavity modes. And so it's the ideal situation of a two-level atom coupled to a single field mode. A two-level atom is basically a spin 1/2. A single field mode is an harmonic oscillation. So it's also the simplest non-trivial quantum physics situation, spin 1/2 coupled to an harmonic oscillator. Because frankly, there is nothing more simple and interesting. Two spins 1/2, it's a 4-level system. You can do everything. You can diagonalize any 4x4 matrix. So you can do anything you like. Harmonic oscillator coupled to harmonic oscillator, it's trivial. Because from a transformation that I wouldn't like to call Bogoliubov, but which is basically that, you can always transform that in two independent harmonic oscillators, eigenmodes, in other words. So the simplest non-trivial situation is spin 1/2 harmonic oscillator. And we see that there is plenty of physics in that awfully simple transition. And the beautiful remark of Cohen-Tanuji, it dates back to the early 60s, to his state thesis, is to say that it's very fruitful in this case not to consider separately the atom and the mode and try to investigate their interaction, but directly work with the full eigenstates of the system plus mode quantum system. And to that, perhaps add perturbations such as spontaneous emission, such as overdrivings. So I will consider a single radiation mode at frequency omega naught, which is resonant or nearly resonant on the transition between G and E. G is the lower, could be ground state but might not be, and E at a frequency omega Eg. And since it's nearly resonant with the same approximation that Philip is using, it's clear that all other levels can be neglected. The good news is that I can get a two-level atom. How do I describe a free atom? I think we have already alluded to that. Two states, EG or plus minus, or 0, 1 in the quantum information science parlance. I don't know one, the mathematician who started quantum information decided to call 0 the excited state and 1 the ground state. It's very counterintuitive. But okay, everybody is sticking to that convention, so let's adhere to it. So you have a two system, you have a basis of Pauli operators with unity make a basis of all possible operators. They have a standard commutation rules. I get rid of the H bars, of course. You can define the spin lowering operator, minus plus, with this matrix, or the spin raising operator, which takes the atom in state G and puts it in state E, whereas the lowering operator does the converse. It's called S plus and S minus in Philip's lecture, but it's basically the same operator, perhaps within a normalization. The most general observable is just the spin in the direction you define in polar coordinates, and it has eigenvectors which are written there. This is, I guess, standard, and I guess you are aware with spin 1/2. Nobody needs a fundamental rehearsal of a spin 1/2. If you do, we could do that later. The interesting point is that when theta angle with pi, with z, describes all possible values from 0 and pi, and phi describes all possible values from 0 to 2 pi, the vector u spans the entire Hilbert space within a global phase and within a normalization. So there is an isomorphism, this is a hard word, but it's called isomorphism, between the whole Hilbert space of a spin 1/2 and the points of the unit sphere. It's called the Bloch Sphere. It's the sphere on which the Bloch vector of this morning is evolving. The north pole is E. The south pole is G. On the equator, it's equal mixture of E and G. On the x direction, it's E plus G. On the y direction, x, E plus IG, E minus G, E minus IG. And all the others have more complex expressions. You are already familiar with the Bloch sphere? Make no mistake, the Bloch sphere lives in an abstract space. Basically, you use, I know that I have to say that, but I don't understand it. You use the SU2 SO3 isomorphism, and your atom is in an Hilbert space of dimension 2. You map it to an abstract space of dimension 3, which might have to see with a real space, but it's not that clear, and you have to take care. The atomic Hamiltonian is just that. Sigma z has eigenvalues +1, -1. So I get an atomic frequency of phi power omega Eg. The conventions are a tad different from yours, but I take the energy 0 at the middle of a transition. And the dipole operator, the dipole is something that describes the atomic transitions. So it drives E to G or G to E. It's paid for that. So it does that with the sigma minus and sigma plus lowering and raising operators. It does that with, it's a vector in space. It's a vector operator. Well, it's a collection of 3 operators corresponding to x, y, z components of a dipole. And the vector is given by a polarization of a transition. This is simply, for instance, uz for a pi-polarized transition, or ux plus I, uy, uy for a sigma plus transition. And d is just a coefficient that I assume to be real, and that has the dimension of a dipole. Okay? How can I treat spontaneous emission for a single 2-level atom? I will add that later to the Drast atom model, but just a word on it. Passing by, 0 temperature. Let's make things simple. At 0 temperature, the only thing an atom can make is spontaneously emit a photon. The only jump operator is sigma minus. If I want the atom population to decay with rate gamma, I have to put a square root gamma there. So the Lindblad equation is that. It is the optical Bloch equation that Philippe used this morning, derives from that if you add, of course, the current driving. Okay? And if you write, well, okay, you have seen that this morning. The population decays with rate gamma, the currents decays with half of the rate, which is kind of weird, but the current has a part in G that doesn't decay. One more interesting thing, and in terms of quantum jumps, one more riddle. This is time. I start from the excited state. Draw me a quantum trajectory. How should I draw it? One quantum trajectory. Ah, he got it in the back. Extra point. At each step, you choose jump, don't jump. If don't jump, you are in E. The non-Hermitian part of the Hamiltonian is just the probability to be in E. So it's an eigenstate. So you stay in E. You go up to the point you decide there is a jump. And if there is a jump, you jump to G. And when you're in G, nothing happens, of course, because no jump is possible. So you stay in G. If you make another trajectory, it decays at a different time. If you have I should go to my dentist. If you average out, you will get the standard exponential. Same thing, and this is radian. Now, this is E, this is P, this is 1. You start from a coherent superposition, E plus G over square root 2. Draw me a trajectory. I should make that a written exam. How is a trajectory? Well, it's written there. Okay, you have no merit. At each step, you have to use the non-Hermitian Hamiltonian, which is basically the projector on E. But E plus J is not an eigenstate of S Hamiltonian. So it does evolve. So each time I make a no-jump evolution, I evolve. And I evolve how? I reduce exponentially with right gamma over 2, with right gamma the probability from being in E, due to this non-Hermitian part. And at some point, I will get the jump. Why is it that? If I have no jump, and imagine that my atom is surrounded by a photodetector, so I can see when the photon is emitted. If I know I had no jump, and if I know that the atom is initially either in E or in G in quantum superposition, if I know there is no jump, that reinforces my confidence that the atom is in G. Let's imagine that the atom has a lifetime 1 nanosecond, and I wait 3 years, which is typical PhD duration, and I still don't see a photon, and I know that my apparatus is perfect. I know that the atom was in G to start with. By not observing, you know something. By not extracting a photon out of a current state, you reduce its amplitude. By not seeing the atom emitting a photon, you reduce the probability for it to be in E. And this is a key important message. When you observe and see nothing, you learn something about the quantum system. This is something that is not often fully realized at the master degree. So I encourage you to think of that and to think, and of course if you are, okay, and then you can write out the complete evolution, which is just the solution of the master equation. Master equation can be integrated with no much avail. Okay? One more example. Just a remark about field normalization. In everything I did up to now, I decided to use a field normalization in which the integral of f squared, the mode amplitude, would be the volume of a fictitious quantization box. But no, I have nothing fictitious. I know with which mode I am interacting. I know that it's the mode of this box made of metal or of mirrors. I know that it's the mode of this laser, which is a Gaussian beam with that characteristics, that waste, that intensity. So I know everything about the mode and its geometry. And instead of putting an abstract, I don't need any longer the abstract box. So I don't know how to attribute a volume to it. So what I do instead is say, at a point where the electric field is an absolute maximum, there can be many points if it's a standing wave, but propagating Gaussian wave is just the center of the waste, the very focal point. For a cavity, it's generally a node of the standing wave pattern. I set f equal 1. And using that, I compute V as the integral of f squared. So it doesn't change anything to the definition, but it allows me to give the physical contents to the fictitious quantization box. And it doesn't change anything in the expression of the field. So I have to write atom field interaction. So I will call C now whatever pertains to the field because, okay, these slides are derived from a Cavity Qed lecture, so C is the field now. Okay. C is F, and F is C. I have a single mode, so I don't need to keep the h bar omega over 2. Just redefine the energy at the energy of the vacuum. So I would say that h bar omega c n for the mode Hamiltonian. The atomic Hamiltonian, I write in it, it's h bar omega Eg over 2 sigma z. And the interaction Hamiltonian is what? The interaction Hamiltonian is minus d scalar E taken at the point, of course, where the atom is sitting. Point R, where the atom is sitting. So I replace D by what I know. I replace E by its expression. E naught is the field per photon in the mode. Polarization of the mode, R f of R minus epsilon c star, R f star. In the F part, which is the mode amplitude, I separate what is the vector contents, polarization, and what is the amplitude contents, the field. And once again, like in Philip's lecture, decidedly we have some overlap, I expand that and I get 4 terms. 2 of these terms are, so to speak, well, all of these terms conserve energy. This is an Jean-Michel Hamiltonian. Energy is perfectly conserved, they are stationary states, but nevertheless it's boring. I dare say that the West Hamiltonian has been diagonalized something like 5 years ago, mathematically. There is an explicit solution of West Hamiltonian, whatever, for all terms, whatever the amplitude of the coupling. It's a mathematical exploit to go there. It's published in PRL, but if you are not a high-level mathematician, you will not get beyond the 3rd line of the paper. But okay, nevertheless. So I explain, I have good terms, so to speak. Sigma plus A describes a process in which the atom goes up by absorbing a photon. I love that term. Sigma minus A dagger, the atom decays and emits a photon. I love that term. In a proper interaction representation with respect to whatever is needed, those 2 terms will be stationary, because basically they conserve the atomic excitation and the field excitation at very close by frequencies. So when you switch to a proper interaction representation, these 2 terms depend slowly on the atom field detuning. Whereas the 2 other terms, atoms get excited while creating a photon, and atoms get de-excited while absorbing a photon. If I go to the proper interaction representation, they evolve basically at omega c plus omega naught. This is fast. And this is also called a secular approximation. When you treat the secular motion on Earth around the sun like equinox precession, you can integrate out the moon's movement because it's infinitely fast at this scale, 27,000 years. So you do the same. When you have an Hamiltonian slow terms and fast terms, you get rid of the fast terms, and you hope that mathematicians will justify up to which level your approximation is right. For most practical purposes, it is very right. It's only in circuit QED that nowadays it starts not being right. I will say a few words on that. So grouping, pushing, pulling, I finally put the interaction Hamiltonian upon this form. A H bar omega naught over 2, A sigma dagger minus A dagger sigma minus. Since I have a minus A here, I need an anti-emission operator inside the bracket. Okay, just a matter of convention. Where omega naught is just basically within polarization overlap. It's just reproduced by the atomic dipole by the field per photon. And I will assume, to make things simpler, that this quantity is real. If not, you can always redefine your levels to make it real. So I don't lose generality. Omega is called, for reasons that we will go on later, is called the vacuum Rabi frequency. And it's a direct measurement in terms of frequency of the strength of the atom mode coupling. Okay? Beware, the field amplitude is hidden in VAs. You have n photons, you have square root of n amplitude. It's hidden there. Or that becomes a complex number when the field is very large, as the boson field becomes a complex number when there are many bosons. See this morning's lecture. Okay, and H is called the James and Cummings Hamiltonian. Dates back from 63. I'm old enough to have seen that. Okay. And it was proposed as a model for a laser operation. It's a very crude approximation for laser. It's a perfect approximation for CQED, as we will see. And so I want to determine what are the eigenstates of this whole field. And just to start with, let's forget the coupling. Let's assume omega naught is 0. And let's look at the eigenstates of an uncoupled atom field system. So this is absolute triviality. The uncoupled states are the states En and Gn, E or G with n photons, Fock state. This is the basis of the whole Hilbert space. And assuming that the detuning omega Eg minus omega naught is much smaller than omega Eg, and of course than omega naught, then En and Gn plus 1 are nearly degenerate. The energy separation is just H bar delta. And the ground state G naught is non-degenerate with everything. It's just alone. And frankly, this ground state is boring like hell. It's boring in the calculations because it's apart. and it's boring for the physics because nothing happens when you put an atom in the ground state in an empty mode. So these are the states. You have G0, that is apart on his own. E0 and G1, separated by delta. For delta equals 0, they obviously degenerate. E1, G2, and if you go up the ladder, En, Gn plus 1. Simple ladder of states. Okay? Now, let's introduce the coupling. The coupling couples G0 to nothing. But the coupling, obviously, the coupling is A sigma plus A dagger sigma minus, or minus A dagger sigma minus. So it switches the excitation from the atom to the field. So it obviously couples E0 and G1. It obviously couples E1 and G2. And up there. But it doesn't couple any E0 with any of the other states in the ladder, because the photon difference is too large. So finally, at the end of the day, your complex Hamiltonian, which is an infinite basis, because there are infinitely many Fock states, twice infinitely many undressed states. Your Hamiltonian reduces to G0 alone. Let's forget it, boring like hell. G0 alone, and 2 by 2 matrices. And if I have chosen to embark on 40 years on Cavity Qed, it is because everything in Cavity Qed boils down to diagonalizing 2 by 2 matrices. And that's an operation that even I master. And so the idea of a dress state is that it's straightforward to compute the full eigenstates of the atom field Hamiltonian just by diagonalizing 2 by 2 matrices. And what is the 2 by 2 matrix? Okay, write it for yourself if you are not convinced. In the proper basis, in the En Gn plus 1 basis, the effective Hamiltonian is delta over 2. There is a minus here, sorry. Yeah, there is an evident minus sign lacking. Please correct the notes. I'm sorry for that. Omega n, it's Emission, so you have eyes to decorate, where omega n is omega naught square root of n plus 1, because there is an omega naught. There is a matrix element of sigma plus sigma minus, this is 1. And there is the matrix element of A dagger, and that gives the square root of 1 plus 1 factor. Okay? And diagonalizing that is not very difficult. This is the energy. These are the states with a mixing angle, which is there. Okay, that's simple algebra. But even if I can get to that point, I find this algebra cumbersome. And I would like to look at simple cases. And there are two simple cases. The first simple case is obviously delta equals 0, exact resonance. And the second simple case is obviously delta much larger than all possible omega n's. Well, of course, delta cannot be larger than all possible omega n's, all relevant omega n's, all the ones where you get a good, decent probability for having that. Okay? No questions? At resonance, plus and minus n are just equal weight superpositions of En and Gn plus 1. If you go in the literature, first, most people don't call omega naught. Most people call it G, and G is omega naught over 2, most of the literature. And most people don't have an I there, because they choose a different phase convention for the electric field. But okay, this is phase conventions, this is, okay, you don't care. Choose one convention and stick to it. That's the good telling for all that. So En and Gn plus 1. How are these states distributed? This is the uncoupled state in the resonance situation. If I introduce coupling G0, nothing happens. I have to diagonalize a 1 by 1 matrix, which is 0. That I can do also. E0 and G1 are degenerate and coupled, so they split. They split by an amount which is h bar omega naught. Sorry, the naught is lacking in this old figure. E1 and G2 split by a quantity h bar omega 2, and omega 2 is omega square root of 2. E3 and G3 split by omega square root of 3, E4 and G5 split by an amount omega square root of 4, and so on and so forth. Okay? This splitting here has two consequences. Imagine that I prepare the atom in the excited state with no photon. This is not an eigenstate of the full Hamiltonian. E naught is a superposition with equal weights of the two rest states. Because the two rest states are superpositions with equal weights of E naught and G. And so this superposition evolves with time because these atoms have not the same energy. It means that if I prepare the atom in the excited state at time 0, the probability for being in the excited state at any time will oscillate between 1 and 0 at the frequency omega naught. This is called the vacuum Rabi oscillation. I plot it, more on that in a second. PE is just oscillating at the frequency omega naught versus time. What does it describe? It describes the fact that an atom in an empty mode can radiate a photon in the mode, reabsorb a photon in the mode, re-emit the photon in the mode for eternity. With 2 photons, it goes square root of 2 faster. With 3 photons, it goes square root of 3 faster. Okay? Another thing is, if you probe the atom cavity system with a weak probe that couples G to E, which is a weak laser field, which is not in the right mode, it's in another mode. You weakly probe the thing. Instead of one line that connects G to E, you will get 2 lines separated by omega. This is called the vacuum Rabi splitting. Okay? What happens if you are very, very high up? If you have Philips laser with zillions of photons in the mode. If you are very, very high up, the difference, you take 2 adjacent multiplicities. This one is split by omega 0 square root of zillions, and this one by omega naught square root of zillions plus 1. 1 being notoriously small compared to zillions, the splitting is constant. So if you are very high up, if you have a very strong current field that you feel in your system, you are in a range of n values for which the splitting is basically constant. If you imagine you prepare the atom in the E state, you prepare it in a superposition of all these rest states. All the superposition evolve with the same Rabi frequency omega R, which is omega naught square root of n, something like that. And you get again that an atom in a very intense field just oscillates between the state E and G with a rate omega R that is proportional to square root of the photon number that is to the field amplitude, which is of course a very classical result that you get very, very classically in 2 lines. What else? Well, okay, if you probe with another, you get, and of course, if you probe the transition to another level, you get a doublet of lines. And this doublet of lines is called the Outler-Tone splitting. It has been put in evidence for atom in a laser field very early in the early times of the laser field, which is just the large n version of the vacuum Rabi splitting that I explained a moment ago. Of course, you may add to all that the spontaneous emission. You may add the fact that there is the coupling to the strong mode, I would say, to the unique mode that we are considering, but there is also background of other modes, other decay channels for the atom. So E can decay to G. And E can decay to G without affecting the photon number in the right mode, because most of the time, think of an optical cavity with an atom inside, most of the time spontaneous emission doesn't enter the cavity, just goes away. So it's easy to show that in this regime, and in the regime of intense dressing, all states in this manifold can decay to all states in this manifold. Just because this one contains E character, this one contains E character, this one contains G character, this one contains G character. So spontaneous emission couples all that. And at the end of the day, if you look at the spectrum that is emitted, you have 4 lines. Those 2 ones at equal frequency, which is the frequency of the atom without dressing. This one at a higher frequency, this one at a lower frequency. And if you look at the spectrum of an atom driven by an intense field in a cavity, what you get is a triplet of line, one unperturbed at the atomic frequency, and two of the sides separated by omega r, which is called the Molo triplet. I made a mistake?
No, you're resonant.
I'm a resonant. Yeah, I'm a resonant. The field is resonant with the atom. All that pertains to the resonance region. Okay? And yeah, okay. Yeah. Okay, the notations might differ, but basically an atom driven by an intense cavity field will emit a triplet of light, which you can understand also in terms of master equation, in terms of sideband created by the Rabi oscillations in master equation. There are many ways to understand that. But you see that in the dressed atom picture, you need not write an equation to get the fact that there is a triplet. You need write equation to get the height of and the width of this peak. This is another thing. Okay? No question yet? Know what happens out of resonance. So this is the position of the dressed levels plus n and minus n, combinations of En and Gn plus 1, as a function of the atom mode detuning. Up to now, I have stayed here at resonance with two dressed states separated by h bar omega n. If I go away from resonance, these states, so to speak, repel. It's a typical phenomenon of an avoided crossing. As a function of the detuning, the uncoupled states do cross at the origin because they are degenerate. And they repel, and they follow branches of hyperbolas. You can tune out the trigonometry, and you will find branches of hyperbola. And you see that as the detuning goes up and up, the plus n state is approaching En in energy, and obviously in wave function as well. And Gn is approaching the state minus n. So very far from resonance, basically the states are no longer, a solid state physicist would say, hybridized. They are not mixed. They are just En and Gn within very small perturbations. But the energy of En is slightly shifted, and the energy of Gn is slightly shifted as well. How shifted are they? In the large detuning limit, you get that, E plus n minus n. And I introduce a parameter S, which is not, I'm sorry, the saturation parameter of Philip. It has nothing to say C with the saturation parameter. It's just the same name by chance. And S is just omega n squared divided by 4. Omega 0 square, I'm sorry. Omega n square, what is my notation? No, it's omega 0 square. Please correct the notes. It's omega 0 square divided by 4 delta. Well, I'm far from resonance. Clearly, I have second order perturbation. Whenever I have second order perturbation, everything can be expressed as the square of a coupling divided by a detuning. So I take the square of the coupling and the detuning, and just for decoration, I use a factor of 4. Okay? Now let's contemplate that. This is the n minus 1 multiplicity, En minus 1 Gn, En Gn plus 1. The dressed states are basically the same, but they are slightly shifted. And of course, as ever, when you couple two states, they get a bit farther apart in energy. So Gn plus 1, this is for positive detuning, is shifted down. En is shifted up. Let's now look at the frequency of all the transitions between these two multiplicities. Let's look at that frequency. Plus n to plus n plus 1, plus n minus 1. It's in fact the transition between En and En plus 1, minus 1. It's a transition in which you remove one photon from the cavity without changing the atomic state. So the frequency of this transition defines the frequency of the cavity in presence of n photons. So you find that the cavity frequency is shifted when the atom is inside. This transition is Gn plus 1 to Gn transition. It's also shifted, and gladly by the same amount. Finally, let's look at the transition plus n to minus n plus 1. It's basically the transition from En to Gn. What is the frequency of the transition from En to Gn? It's the atomic frequency. You don't change the cavity photon number. It's the atomic frequency. It's the atomic frequency in presence of a cavity field. And you find it also different from the atomic frequency that you have without the cavity field, which is there. At the end of the day, if you make all the algebra, you find that in the cavity, the atomic frequency is shifted by an amount, which is this S, omega naught square over 4 delta, times 2n plus 1. This is a combination of lamp shift and light shift. First, you have a term that is proportional to the field intensity, n. The atom transition is shifted by something proportional to the field intensity. It's called a light shift. If you put an atom in an intense light, its frequency is changed. Since its frequency is changed, its energy is changed. And this is very much, in the intense field limit, the origin of a dipole force that Philippe was describing this morning. If you put an atom in a strong red detuned laser field, it loves being at a minimum of intensity because it lowers its energy. This term is more puzzling. These terms exist even when there is no photon. It means that inside the cavity, the detuned cavity, the state E naught is shifted. Why is it shifted? Because E is coupled to the vacuum fluctuations inside the cavity. This is what is called the lamp shift effect. As you know, the lamp shift, or as you should know, the lamp shift is the difference between the 2s and 2p levels in hydrogen. It's about a gigahertz. And it's due to the fact that the 2p level has spontaneous emission. This is the delta we have seen in the spontaneous emission problem. Properly renormalized, it's finite. And since finite, it is a gigahertz. Here we see the same thing, but we have a single mode. There is no ambiguity, there is no divergence. We just have a shift due to the vacuum fluctuation. Okay? And of course, G naught, nothing happens, nothing is shifted, no lamp shift, boring like hell. So this is a combination of light shifts and lamp shifts. At the Kessler time, the light shifts were called lamp shift because they were not using lasers but lamps, spectral lamps, and so it was called the lamp shift. And I think the joke originates directly from Kessler. Now, we have also seen that the cavity frequency is modified. And in fact, if you look at this modification, it's independent upon the photon number. So really, just the whole ladder of states that get shrink or expanded a little bit. And if you work out, you find that when the atom is in E, the cavity is shifted by S. When the atom is in G, the cavity is shifted by minus S. What is that? This is the single atom limit of the index of refraction. When you put a transparent matter inside a Fabry-Perot cavity, this is a very bad idea, the cavity gets out of alignment. But imagine you do. You change the effective cavity length. So you change the mode frequencies. Here we have one atom. One atom that is detuned. Meaning that, of course, I didn't say it, but it's clear from that there is no atom field exchange. Plus n remains plus n forever, and it's En. If you put the atom in the excited state, it remains in the excited state. Cannot emit photons in a detuned cavity. That wouldn't conserve energy. So it means that my atom is unable to exchange energy. It means that my atom, it's not my atom, it means that the atom, you never own an atom. They have been there for 15 billion years, and whatever you do to them in 10 seconds, it won't affect their life for long. The atom is unable to absorb radiation, so it's just something that has an index of refraction that shifts accordingly the transition frequency. And what is remarkable is that it's possible experimentally to achieve conditions in which the single atom index of refraction is measurable. Generally, you need 10 to the 23 atoms to see index of refraction of the windows there. Okay? Questions on the dry atom? Now, let's make it fun. Let's go to Cavity Qed. I'm oscillating around, okay? I'm trying not to enter too rapidly in Cavity Qed, which is, of course, my pet field in physics. But let's go to it, and let's see how we can play with a dressed atom model in that context. More questions, more remarks. Yes?
I mean, so for the, can you turn off the dress state?
The resonant ones?
No. The one with the cross.
Yep.
So I understand that you say this one is related to X, right?
Sorry?
The X-axis.
The x-axis is the atom cavity detuning in units of omega n.
Yeah, I mean, I understand that it's zero, which means
Which means exact resonance.
yeah, and I think means the S is infinite. S.
No, at resonance, S only applies in the dispersive regime.
Okay.
It's what is called the dispersive. It's the far-off resonant regime, because to get S, I use this approximate formula for the energy, which is only valid in the limit delta much larger than omega n. Okay. How does we might allude to that. In fact, if you go closer to resonance, S increases, but at some point the index effect saturates and becomes just the shift due to the dressed atom. Everything is continuous in physics, no singularities. Okay? Good question. Thank you for asking it. No problem? So let's go for half an hour of Cavity Qed. Ready for that? It will be more experimental. You will see signals. So it will be more, hopefully more palatable. Let's get rid of that. It's very hard to manipulate a mouse that you don't see. And let's go to the final part of this lecture, which is Cavity Qed. So there will be basically 5 parts, a short introduction giving you a bit of historical frame of Cavity Qed, a bit of discussion of the experimental tools, and a few, I would say, notations pertinent to the theoretical tools. And not surprisingly, we will cover resonant interaction, dispersive interaction, and if time allows, say how the thing will evolve in the future. Cavity Qed is so the art of coupling a real field held in a cavity, the equivalent of Einstein photon box, with a single two-level atom. And this is by far not a recent thing. The original remark is less abstract by Purcell. This was the time the book of abstracts of the APS March meeting was only 20 pages long. Now in the last March meeting, there were 12,768 participants. I didn't count them myself. APS provides for that. So the abstract would be a tad longer, like 100,000 pages. And Purcell went to the APS March meeting. Purcell is the pope of NMR and of electromagnetism. And he said, Jesus, if I take a spin in NMR, the frequency is in the radio frequency domain. So the matrix element is not good, so the lifetime is basically infinite. It's many ages of the universe. But if I put the spin in a resonance circuit, an RLC circuit, but it's a cavity, basically. If I put it, I could speed up the emission by a big factor, which is proportional to the Q of my resonant tank circuit. And this is very much the start of Cavity Qed. The recognition that spontaneous emission rate, that I computed the d square, this is right in free space. But it's not God-given or universe-given. If you can change the limiting conditions imposed to the field, you can change the mode structure of the field, and if you change the mode structure of the field, you change the sum in the kernel, you change gamma. And so Purcell suggested to speed it up. So this is a very brief but very seminal paper. And Dan Kleppner in 81, a bit later, suggested to slow it down. Put an atom in the cavity which has no mode at the atomic frequency, the atom will stay excited forever. It cannot decay, there is no mode to decay. Well, ideal cavity, ideal atom, of course. And that started the whole stuff. Generally, people distinguish in Cavity Qed 2 regimes. The so-called weak coupling regime. in which basically you still have a spontaneous emission, in which basically you alter the properties of the atom, but you change the spontaneous emission rate, you change the shifts, but you don't change them qualitatively. And the strong coupling regime, in which the atom cavity interaction dominates, in which, for instance, you would be able to observe this Rabi oscillation phenomena. And of course, we will see the. So two regimes, which doesn't mean weak is weak, of course, but it doesn't mean that it's not interesting. VCSEL lasers, many photon emitters of solid state, are based on the weak so-called Purcell regime of modified spontaneous emission, and it has a huge possibility for technological applications. This is perhaps the first experiment on the weak coupling in which we observed in '83, that's some time ago, in which we observed in '83 that we can speed up the spontaneous emission on a microwave transition between two Rydberg states, just by putting them in a cavity. Almost at the same time, Gabriel C. and Demelt on the one end and Hewlett, Hilfer, and Kleppner observed the spontaneous emission slowing down. This is weak coupling regime, still a spontaneous emission, still an exponential decay of the atom. The real first experiment of a strong regime was performed by the late Herbert Walter in Garching and by his now student Dieter Mechele. He is now president of the DPG, so you see that the time flows and close to retirement himself. And they run what is called the micromaser. It's a laser that operates. It's a laser that operates with Rydberg atoms, a superconducting cavity, and in which you maintain a sizable field in the cavity, in spite of the fact that one atom crosses it from time to time, but at very long time intervals. But the cavity is so good that you can maintain a maser oscillation. And this is very much the first experiment in that. How do you find the strong and the fast coupling? Of course, you have to consider time scales. What are the time scales? We already know about them. There is the atomic level lifetime, 1 over gamma. There is the cavity lifetime, 1 over kappa, the lifetime of the energy in the cavity, the lifetime of a one photon state. There is the atom cavity coupling, omega naught, which is the inverse of a time, within pi. And there is the atom cavity interaction time. How long does the atom stay in the cavity? If you want the strong coupling, you need that the interaction time tan omega naught is of the order of 1, so that the atom evolves. But you want all these times of the resonance and interaction to be much smaller than the decoherence time. And how is it achieved? Nowadays, Cavity Qed flourishes in 4 different directions. It's not in historical order, but there is optical CQED. In optical CQED, very much represented by the groups of Jeff Kimball in Caltech or Gerd Trempe in Munich. You put an atom with an optical transition, alkali atom, because, okay, they are simple, inside a very high finesse Fabry-Perot cavity. And you achieve a strong coupling regime. The damping rate of the cavity is pretty high. It's kilohertz. The lifetime of the atom is short. It's typical transition of an alkali. But the interaction time can be extremely long thanks to atomic cooling and trapping techniques. And the coupling is extremely large if you go to a micron-sized cavity. So you get the strong coupling regime easily, with beautiful applications to quantum information processing, single photon entanglement, atom photon entanglement. You have to read all the literature. Of course, the people who are there with applications say, well, this high vacuum tank with 2 tables of lasers and 5 postdocs, it's not possible to put it in a device. So they develop what is called the solid state CQED, in which basically you replace the atom, for instance, by a quantum dot, kind of artificial atom, with some limitations. And the cavity is, for instance, one of those micropillars with Bragg mirrors and a confinement, like in an optical fiber, along the axis. And then everything goes much faster. The interaction time is infinite, of course, because it's a device. And as long as you don't put your finger on top, it remains there forever. It's very fragile. But the decay rates are enormous, gigahertz, but the coupling is gigantic. So they also achieve the strong coupling regime. And of course, you can think of optically pumped vat. There are beautiful experiments by Pascal Senella in L2N in Orsay about that. And Hitachi Mamoglu and others. A new flourishing, and I will say a little bit more later, is circuit QED. In circuit QED, you take the same artificial atom approach, but instead of solid state, of standard devices, you use superconducting circuits. In good situation, a superconducting circuit behaves just like a two-level atom. And you couple them to cavities in the microwave domain, for instance, embedded on a superconducting chip, very, very high Qs. And this is a very, very good choice, which was first investigated by Rob Shelkoff in Yale, and which is now the subject of a thriving intensity worldwide, activity worldwide, Nakamura, Martinez, Devoré, and many others, who are in Lyon. The interaction time is infinite. The damping rate is very, very small. And the coupling is absolutely gigantic. Because an atom has a dipole which is its size. The superconducting circuit has a dipole which is its size. But the size can be millimeters. So you can make enormous dipoles and enormous couplings. And finally, my favorite one is microwave CQED, in which you use real atoms, but very specific ones, circular Rydberg atoms, superconducting cavities. You have a very small coupling, 10 kilohertz, infinitely smaller than this one. But you have exquisitely long damping times in orders of seconds. So it's a very peaceful, very calm experiment. Everything processes at a millisecond time scale. You have plenty of time to think when you make data taking. Well, you need very many time to think when you make data taking. In this lecture, I will focus on microwave QED, just because it's the field I know more. And we won't need anything about superconducting circuits, Josephson junctions, and things like that, which are far from my expertise. But of course, everything I will say in this frame exactly fits with the other frames of Cavity QED, mutatis mutandis, by scaling the frequencies, by scaling the damping, by scaling everything. So a little bit of the tools of Cavity QED. As I told you, we use very, very specific atoms. We use the circular Rydberg atoms. What is a Rydberg atom? It's an atom with a high, you know the quantum numbers of the atoms, I guess. It's the only thing I will require in atomic physics. A very high n, principal quantum number. Typically, we use around 50. It's a good choice. I will explain why in a second. But moreover, we put the electron in the state with maximum L and M values. L equals M equals n minus 1. If you think of classical terms, the orbit with the maximum angular momentum is the circular orbit with this energy. In quantum terms, the orbital is just a torus centered on the classical orbit. It's a very classical atom, finally, because all the quantum numbers are large. And if you invoke Bourian way, the correspondence principle, it tells you that everything in these atoms can be computed classically. Which is good news because they are also very good for quantum experiments. So there, we have chosen by chance the transition between 51 circular and 50 circular, which is at 51 gigahertz. The rationale of the choice is that the only transition where the frequency is gigahertz is equal to the principal quantum number. Think of it, there is no other one. So this is the reason of the choice. It's at 51 gigahertz. Well, it's high up in the electronic, but it's okay. It's still within the electronic. And there are plenty of good properties. The lifetime of this level is very, very long. They are very excited. You are very close to the ionization limit, but yet the lifetime is of the order of 30 milliseconds. Why that? Classical physics. You have a circular orbit. The acceleration of the electron is at a minimum compared to all possible orbits with the same energy. If you're on an elliptic orbit, you have a very strong acceleration when you come close to the center. Larmor formula, the power dissipated by an accelerated charge is proportional to the square of the acceleration. You understand that this atom dissipates infinitely less energy than this one. So this atom has a much longer lifetime. Well, you can also put that with the proper D's and omegas. Huge dipole matrix element, n square. The size of these atoms is 50 square times the size of a hydrogen atom. So it's a quarter of a micron across. It's about 10 times the size of a standard virus. It's a big thing. It's larger than, and since it's big, it has a strong dipole. This is good for the atom field coupling. Remember, D E naught. I want a large E naught, I want a large D. H bar is what it is, except in U. I can tune the transition using the Stark effect. This is good for practical use. And I can detect these atoms very easily and very sensitively and know in which state they are at detection. Just because these atoms, the electron is bound by a very small electric field. At 50 square atomic units from the center, the field, the Coulomb field, is of the order of 150 volts per centimeter. The field in a power plug. So if you put the atom in that field, it breaks. And if it breaks, you get an electron that you can accelerate and detect easily. And the field in which the atom breaks is not the same for level E and level G. So not only you detect the atoms with unit efficiency, or close to unit efficiency, but you can also tell at detection it was in E or in G. But that's beautiful atom. Okay. And of course, you need to couple them to cavities. And so you need a cavity at 51 gigahertz. How do you make a cavity at 51 gigahertz? The electrics, no use. Wavelength 6 millimeters. A lambda over 4 plate is 1.5 millimeters thick. It will never do it. Moreover, these atoms are very sensitive to stray electric fields because they have a large dipole. Better not use. So you go for a metal. A metal is not that bad, but not that good neither. So you have to go to superconducting metal. Because superconductors are perfect at 0 frequency. At finite frequency, they are not quite perfect. Why? This morning's lecture on BEC, basically, well, it's not exactly more complex than a BEC, but the electric field penetrates a bit in the material, and in the material there are such things as unpaired, uncondensed electrons. So we have a residual loss mechanism. But it's not serious, and we have built cavities with niobium cotton mirrors, and the record what we have is holding a photon 0.13 seconds. The cavity is about 3 centimeters across between the mirrors. The photon makes, in this 0.13 seconds, 40,000 kilometers between the mirrors. Meaning that if you envision, which is totally wrong, the photon has the ball is bouncing 1 billion times on each mirror, which is a lot. Okay? So we can say without fear that these are the best mirrors ever. Optical mirrors typically bounce 1 million, 10 million times at most. But of course, they have no use. So it corresponds to a Q of 42 billions and a finesse of 5 billions, which is decent. How do we make the mirrors? We spend, I just say that, it's very technological, but we spend 20 years on making mirrors of various shapes and various with our own Moore law, winning an order of magnitude over 5 years. Basically, we take copper, and copper can be machined to nanometer accuracy. And this is a torus. We need a torus for not obvious reason. This is a torus machined to nanometer roughness and 100 nanometer absolute accuracy. And this is 5 centimeters across, and it costs 1,000 euros. So, you can machine copper as you wish. Of course, copper is not superconducting. So what we do is that we go to a vacuum chamber. This is a niobium rod. We light a discharge. This is heated to 4,000 K. Niobium evaporates and covers the copper. And if you are lucky enough, it doesn't peel off when you cool down. And then you cool down to low temperature, as low as you can. Low, why? To get the transition temperature, 9.2 K. Well, more like 8 K because it's a thin film. Low enough because you want also to cancel the thermal fields. A 50 gigahertz photon amounts to a couple of degrees. So if you are below 1 degree, you get rid of most of the thermal photons, which is good also. And vacuum, and it's also good to go to low temperature for the vacuum. So you put that mirror in a cryogenic environment at 0.8 K, and this is the scheme of the experiment. An atomic beam, fast atoms, no cold atoms, In a cold atom school, I will speak of experiments without any cold atom. Well, to some extent, we will have cold atoms in a raging box in which we prepare the circular Rydberg atoms. Not that easy. They have 50 units of angular momentum. A photon has 1 unit of angular momentum. So basically, you need to coax a rubidium atom to ingest 55 photons. We lose a little bit, 53 photons. And there are laser photons, radio frequency photons. If you are interested, I could give you details ad nauseam about the right way to prepare circular states. They interact with the cavity mode, and we detect them. And just before and just after interaction, we can, with classical radio microwave fields, prepare the atom in any Bloch state on the Bloch sphere, or rotate it as we wish before detection, which means detecting any direction on the Bloch sphere. There is an RMP paper. So this is the artist's view. This is the student's view. 40 kilograms of copper, niobium, and shields cooled down to 0.8 K. Staying cold for, now we have been cold for 4 years and a half, I think. Because the cavities are surfaces, they are extraordinarily fragile to contamination. So when we get cold, we remain cold for years. Meaning that every 47 hours, somebody has to go in the lab to fill the helium tank, including New Year's Eve. And now our students and our male and female students having girl and boyfriends, we have advocates, artists, actors, we know how to fill an helium tank. Much more recently, there is one drawback in this experiment that the atoms, here it's a thermal beam, rubidium, typical velocity 250 meters per second. We can select the velocity with optical pumping, but okay, never care. So the atoms go fast. Going fast is a good thing if you want to get a lot of information from the cavity. Once again, what we detect is the atomic state at the end of the interaction. It's the atom that gives information about the interaction. The more atoms we send, the more we get information on the cavity field. This is interesting. But of course, the interaction time is limited. The waste here is 6 millimeters. Typically, the atom field interaction time is tens of microseconds. So it's short. And for some experiments, it's a problem. So we have built another experiment, cold atoms, with a cold atom beam at 8 meters per second entering a superconducting cavity. And with that, we can achieve a very long, hundreds of microseconds interaction time. Much more on that later. Okay, how do we adapt the general formalism to this circumstance? Well, really nothing. We just need the mode shape. The mode shape is the Gaussian standing waves with a waist W naught, which is 6 millimeters, very close to lambda. It's a very open mode. And 9 antinodes along the axis. And so you can compute the cavity mode volume. It's a simple exercise in Gaussian integration. And you get that it's just the surface of the mode times the length of the cavity, within a factor pi over 4, which is very close to 1. So from that, you can compute, so the volume is 0.7 centimeter cube. And from that, you can compute the field per photon, which is 1.5 volt per meter. It's a rather large field. When the atoms flow through that, of course, they see an f of r, a mode envelope, that is a Gaussian. So they slowly couple in and slowly couple out the mode. And in everything I discussed so far, the Rabi oscillation, the dressed atom, I assume that the atom is sitting at one fixed position. Here they cross. It makes a little bit complication, but not that much in the strictly resonant case and in the strongly dispersive case. For a resonant case, it turns out that the Hamiltonian is just multiplied by a Gaussian function of time. And so, getting the evolution operator is just basically replacing the real time by the integral of that over the real time. And it's basically defining an effective interaction time that just takes into account the Gaussian variation. Yes?
How do you change the resonance frequency of your cavity?
This is well, we change it mechanically. We have piezos that define the spacing between the mirrors. This is a good question. I should have asked it before. There are piezo tubes there that are used to slightly change the cavity. Of course, they have a very limited range because piezos don't operate well at 0.8 K. That's a thermodynamic effect. They are 10 times less efficient than at room temperature. And so you'd better have a system here that is mechanically reproducible to a fraction of a micron, which is not that easy. Generally, the cavity is just on the edge of the tuning range, and you have to open to put a bit of tightening on the screws to get a few microns alignment, cool down again. Well, it's a nightmare. Okay, but never mind. So we can define an effective interaction time. I skip the details. We won't care with that. In the strictly resonant case, because the evolution operator is simple, and in the dispersive case, because you can define an effective Hamiltonian, which is basically sigma z n, and which is just multiplied also by a function of time. So let's skip that. As I told you, our system is very close to the system of circuit QED. And I would like to say a few words because it's the thriving field now, and most probably those of you who would like to embark or have embarked in cavity QED studies are looking at circuit QED and not at microwave cavity QED. Why is it that? Because you can work out circuits based on Josephson junctions which have very beautiful properties. The most popular one is called the transmont. And the transmont is a very simple circuit. It's a big condenser with two plates. These are two isolated electrodes, which are linked here with a small loop with two Josephson junctions, which is a screw. And for reasons that I don't want to describe here, and I would be totally unable to describe them in details, this thing in a proper setting behaves as a nonlinear oscillator. Meaning that if you are at a frequency that is close to the transition between the ground and the first excited state, it exactly behaves as a two-level atom. And it does so with exquisitely long relaxation times, up to tenths of microseconds. Those guys between 2003 and now have won a factor of nearly 10,000 of the relaxation time of our devices. So it lives for long. With what cavity do you couple them? Well, either real cavities. This is what is called a 3D pillbox cavity. It's just a block of aluminum. Poor aluminum is superconducting below 1.5 K. It's poor aluminum, and you have a cavity, and here on this chip, you have your transmont device. And you see it has big ears, big antennas that result in an extremely large coupling to the field. Or you can use, instead, a strip-line cavity. This is a kind of flattened coax cable that goes like that in a serpentine way through the chip and behaves as a piece of open coax, so it's a cavity. And if you have a complete setup, this is one thing that has been used, for instance, in Saclay, with two transmonts and two cavities and readout resonators, and they can integrate now tens of these cavities and tens of these transmonts on a single chip. So it's very beautiful. Circuit cavity and Rydberg atom cavity, QED, have very, very similar properties. Basically, they both operate in the microwave domain. We are 50 gigahertz, they are typically 5 gigahertz. The only difference is that they need to cool down a little bit more than us to be in the low photon number regime for the thermal field. They cool down to 20 milli-K with different fridge, while we cool down to 0.4, 0.8 K with helium-free fridge. Okay, the difference is not that big. Both are in the microwave domain. They have much higher atom field coupling because they have atoms that can be millimeters across. But they have also a bit faster dissipative processes. And of course, they have infinite interaction time because the chip is there for months when it works. Mutatis mutandis, if you put everything together, they have very similar achievements. We'll see signals of Rabi oscillation in Rydberg cavity, which compare very well to the signals of Rabi oscillation in circuit cavity. Their dispersive interaction compares with ours. At the end, they are very similar. Of course, circuit QED is more integrated. Okay, and it's really a thriving field worldwide. There are many, many groups working in circuit QED. Okay, so now, and next to tomorrow, in fact, I see that Mathilde is worried. Tomorrow we'll go to the resonant interaction and look at the vacuum Rabi oscillation. And we will look also at the Rabi oscillation in the mesoscopic field, current field with a couple of photons, say 10 photons, because we will see that there is a lot of interesting basic physics there. And then we will enter the dispersive interaction and go through the Schrödinger cat zoology. We raised a lot of Schrödinger cats, kittens, cats and lions, and tigers and bears, and we will discuss a little bit those cats. So, thank you for your attention. If you have any questions. Questions? No questions? Boo. They are just dead. I killed them. The mad scientist, I will kill them all, and he pushes the big red button. Okay. Leah, thank you. Please remind me to make the check for you tonight.
You gave us a classical explanation for the particular stability of the reverse, this circular reverse. And how can we, quantum mechanically speaking, understand this regarding the formula reverse of gamma that depends on omega t? I mean, it should be d squared, right?
Yeah, d square omega cube. This is the key. All the rest is h bar c and things without interest. Let's look at the scaling laws. It's very interesting for the Rydbergs to always look at the scaling law as a function of n. D is the size of the atom. The size of the atom is n squared, because this is the radius of the Bohr orbit, Bohr model. So d squared is like n to the fourth. Omega is like the energy between Rydberg states. The energy of a Rydberg state is r over n squared, where r is the Rydberg, minus r over n squared. So the difference between two adjacent Rydberg states is 1 over n cubed. So omega cube is like 1 over n to the 9. Yes, there are very high powers in the Rydberg state property. The dipole-dipole coupling, Antoine Brouwer will speak of that, scales as n to the power 11. So getting one more n makes a lot of difference. And at the end of the day, gamma is like 1 over n to the 5. So this is long. This is the analytic reason. Why is it much longer than all other Rydberg states? If you look, this is the ground state. This is the 5s for rubidium. This is, let's say, the 50s Rydberg state. And this is the 50c Rydberg state. If you compute the 50s Rydberg state's lifetime, it's about 200 microseconds. Why is it that short? Is that the main decay channel, 50p, sorry, selection rules. The main selection channel is a direct decay through hard UV photon towards the ground state. The matrix element is bad, but omega cube is really large. It's 1,000 terahertz to the cube. So it decays fast, relatively fast. Whereas the circular state, selection rules, where can it decay? It cannot decay to the ground state. There are 50 units of angular momentum difference. And okay, decaying with a 2 to the 50 pole transition is not very likely. So in fact, it decays only to the 49C, which is just 50 giga or 53 gigahertz apart. So the only decay channel for a circular state is the transition towards the neighboring circular state. So what I gave is the classical version of the argument. This is the scaling version, and this is the full quantum picture. And of course, all these arguments give the same numerical figures when you put everything in. Correspondence principle. Yes?
When you prepare this ring shape, like, do you have any magnetic field? Otherwise, how do you break this symmetry?
Well, I have been elusive because I don't think this lecture should be about atomic physics. But clearly, the circular states have one problem. They break the spherical symmetry of the hydrogen atom. It's a flat atom. It's a flat tire. Imagine a long spaghetti pasted onto itself. If you put it in free space, it will make knots, most probably. So you have to put it on a plane to conserve it. And we have, if we want to conserve the circulars, to put them on a plane. The right interpretation to that is that in zero fields, the circular state is degenerate with the 2,500 levels in the hydrogenic multiplicity. Any perturbation, any action of anything will mix the circular state with all the other states in the multiplicity. And that corresponds to this idea that the state is wrapped up in something dirty and very unfriendly. How do we get rid of that? We put one electric field. We define a quantization axis. We give the atom a direction to follow. And then the circular state, which orbits in a plane perpendicular to this electric field, will remain circular forever. How large should be the electric field? Well, large enough to overwhelm all parasitic fields, typically 100 millivolts per centimeter at least. How can it be large? It can be large, in fact, up to the ionization threshold. You can draw a circular state all the way near to the ionization threshold, get back, and it's still purely in a circular state because it's coupled to nothing. That's the way we do that. We break the cylindrical symmetry, the spherical symmetry. I've been very fast on that. You could also put a magnetic field. But an electric field is, well, electric field acts on charge more than magnetic fields. So you will need 100 Gauss to make what 1 millivolt per centimeter does, 100 millivolts per centimeter do. And never, never ever think of putting a circular state in a field, in a zero field. It won't last. Yeah, sure. I could speak a few hours more, of course.